name is Evan O'Connor, and I am a research mechanical engineer at the Cold Regions Research and Engineering Laboratory in the U.S. I'd like to thank the workshop organizers for inviting me to give a talk at the workshop. And before I get started, I'd like to acknowledge my co-authors who are listed here on the talk, in particular Brennan West, who worked on quite a few of the simulations that I'll be presenting in the talk today. In my talk, I'll be speaking about our work modeling continuous sea ice flows with the discrete element method. I chose that title because in our group we've been thinking a lot about how do we use discrete element methods, which make a lot of sense for modeling sea ice at the scales we're interested in, but how do we accurately capture the stress in the ice? How do we propagate cracks or leads in the ice using these kinds of methods? So understanding this a little bit better. Continue. So at CREL, we're part of a larger group of researchers that we call the Sea Ice Research Center. It's a collection of field scientists, remote sensing experts, modelers like myself. And when we talk about modeling sea ice, we're particularly interested in this technical or regional scale, where we know that these assumptions of sea ice acting like a continuous material start to break down. And using discrete element methods and treating the ice as a granular material seems to better capture the dynamics and the emergent behavior of the ice at this scale. But there's a lot of challenges associated with modeling ice using the discrete element method, or modeling ice generally. And some of the things that I want to highlight here that we're particularly interested in is how do we accurately predict flow scale stresses in the ice? What are the conditions and criterions under which the flows fracture? Given forcing conditions from the atmosphere or the ocean, how can we do near-term forecasting? This is something we've been looking at quite a bit. And importantly, and I hope this is something we can talk about at the workshop, is how do we validate our predictions? We've been trying to find characteristic ice dynamics in either through imagery or whatever we can find to try to come up with good validation examples for our simulation tools. In other communities, in the mechanics community, there are lots of tests that one might run, compact tension or others, where you can test your models against, and we're trying to find those analogs in the sea ice as well. And so obviously our overarching research goal is to develop these computational tools that accurately represent the ice dynamics. Okay. And so in support of our efforts, we've developed an in-house discrete element code that we call particles. It's a particle-based method, so under the hood we have a discrete element engine, and recently we've also implemented a peridynamics engine, which is very similar to other particle-based methods with some slight tweaks, and it came out of Sandia National Laboratories. Our code is really purpose-built for modeling sea ice dynamics, but it could be used for granular media generally. We have spherical, non-spherical particle geometries, as you can see on the right-hand side in the video. Rigid and cohesive contact laws for particle breakup and contact between particles. All right, and so I just want to go over some of the salient features that we focus on at a very high level when we talk about modeling sea ice dynamics with the discrete element method. The first thing is initializing our simulations with from satellite imagery. The second being, how do we do particle-to-particle interactions? What sort of contact laws or cohesive contact laws are we using? What are the atmospheric or ocean conditions that force the model? And lastly, how do we update the dynamics? What are the equations that we're solving? And I'll go over each of these 4 bullet points in detail going forward. All right, so at CREL we've developed some tools where we can initialize our simulations from satellite imagery, and this is just a very quick overview of how we do that. So on the right-hand side, we've got an optical satellite imagery we have of the Nares Strait, and then what we do is we do a land mask, and we highlight just the ocean and ice region here, or I think in particular actually the ice, and then we do a Voronoi tessellation of this region, highlight the ice itself, and then we clip those polygons to the ice boundary, and what we're left with is a discretized version of the ice seen in the imagery. And then we use this to initialize our simulations. And the second and really important aspect of our code is how we handle momentum transfer from the atmosphere and the ocean to the ice. Currently, we're using what's most often done in the literature is quite simple atmospheric and ocean drag laws that you can see in the equations in this slide that we've implemented in the particles or in our code. And basically what it does is it takes some drag coefficient, the particle size, and the particle velocities, and updates the forces accordingly. We use pressure ridging-based contact laws to model interparticle contact when we're modeling sea ice. We use the model that was developed by Mark Hopkins at Krell back in the 90s. These methods that he developed were kind of a homogenized method where he did very small scale simulations that you can see on the right hand side here of two flows coming into contact. And based on the results of this simulation, he was able to develop contact laws that could be used in a discrete element simulation where this local behavior is essentially homogenized out, and it's the overlap areas here indicated by these A's here between the particles that now capture the ridging and energy dissipation that's happening in these kinds of contact laws. There are other approaches in the literature from Andrew Roberts at Lannel for use in continuum models, but there hasn't been a lot of improvements in these kinds of contact models since Mark's work, and I think there's quite an opportunity here to also improve how we model interparticle rigid contact for sea ice in discrete element methods. The thing that I've been thinking about a lot and methods that we've been developing at Krell to improve how do we model larger flows with the discrete element method where we might want to, say, break up some of these larger flows into mini discrete elements. How are these discrete elements connected to each other to approximate more of a continuous-like material that you would expect this larger flow to behave like? And how do we basically go about doing that? So how do these particles interact, right? And so there's a number of ways to do that. The way we do it in our code is we added this so-called cohesive beam model, and what that basically does is it approximates or uses the equations of an Euler-Bernoulli beam, and there's no obviously physical beam in the model that connects these two particles, but we use these beam equations to approximate the force and moments that are acting on the particle. So you can see this blue beam and these different coordinate systems that are idealized here on the right hand side image. And so depending on how these particles rotate or move away from each other, there are some kind of cohesive forces that try to keep them together, as you can see in the video in the lower left. Of course, the beams can break, and we obviously want that to happen if we're going to be able to model fracture. Most often, these what I'll call local bond-based failures are used, and most often they are strain-based or stress-based, as you can see in the equations in the lower right-hand corner. So there's usually some kind of criterion that, some sort of separation or maximum stress that's exceeded, and then we break the bonds, and the particles are allowed to move away from each other. And then at that point, our rigid contact laws are activated, and so if these particles then do come into contact after the beam breaks, the supplementary contact laws take over. One thing that we're excited about and that we've been thinking about quite a bit is extending these methods to look at calculating stresses in these discrete element methods through a non-local approach. And so this is what we've been doing in our code and how we calculate stress currently. And so the way that's done is shown in this sort of figure here in the lower left. And the equation to calculate stress is shown here in this equation right here. And what happens is that we calculate the inner product between a vector that connects the centroids of the two particles that are cohesively bonded and the force vector that acts between the two particles calculated through these cohesive beam equations. And between the dyadic product of the branch vector and the forcing vector, we can calculate an actual stress tensor. And the great thing about now we having this stress tensor is now we can use any sort of failure surface. We can calculate von Mises stresses, we can calculate principal stresses, and so we can use more traditional failure methods that are not often available in these kinds of discrete element contexts when we're thinking about local failure. And so it's non-local because we're including the influence of all of the nearest neighbors here, okay? So what happens if the stress we calculate exceeds some sort of criterion? Well, what we're doing right now is we'll calculate the direction of the largest tensile stress, create a clipping plane that's indicated by this dashed line that's perpendicular to that direction, and then we'll snip all the beams that's indicated by these red X's here that are on one side of this plane to create the failure surface. So in this case, this center particle had exceeded its stress threshold. We create its failure plane, and then we snip the bonds. Okay. And again, the criterion that's used here is we'll evaluate the stress against some sort of failure surface. So on the right here, we're seeing some sort of failure surface from Schreier et al. In 2006 with this like a more Coulomb type failure surface. And that's what we use as well in our code. Okay. One downside with using these beam-based or lattice sort of particle cohesive methods is that there's a calibration procedure that needs to be done. If you want to prescribe the stiffness, say the Young's modulus or the Poisson's ratio, these elastic properties at the effective level, and then the connection between the local beam modulus and the overall effective modulus isn't known right away. And so there's this calibration procedure that needs to be done. So if we want the overall flow to have some kind of elastic response, we need to do a calibration procedure to set these local beam parameters such that we get the overall effective response that we would expect. Okay. So there's some pre-processing here that's a little bit tedious, but once it's dialed in, it's done, and we can run a number of simulations. But we've been thinking about other ways to move beyond these kinds of calibration procedures, in particular using peridynamics instead of these cohesive methods, and we've had success there going forward. Similarly, besides the elastic properties, we also need to calibrate the failure properties, and so what we can do is we can, say, compress a column of ice and try to tune our local failure parameters or our non-local failure parameters such that the overall effective failure stress is what we would expect, or at least what we would want to prescribe. So we would take the value from the literature for sea ice at the scale of interest, and we would try to calibrate our failure stresses against those values. Okay. So now I just want to talk about a couple of examples of our current work, and I'll go through these fairly quickly. Like a number of other researchers, we've been interested in the Nares Strait because there's some really interesting ice dynamics that happens in this region. It's located up, you can see in the picture on the left, in between Greenland and Canada. This region here of interest, Nares Strait. And so this region is of particular interest because as the ice continues to thin due to climate change, these ice arches that form in the Nares Strait, which previously acted like a plug for multi-year ice that were usually in north of this strait area, now can flow out when these ice arches break due to the instability and weaknesses of the arch due to thinning ice. So there's some interest here how if we change the sort of strength of the ice, what are the conditions under which these arches can break, and then you would get ice flowing out of this region. All right. So to start with, we looked at a couple of idealized channel geometries, and this work was inspired by Dansereau et al. In 2017, who did something similar for their continuum model that they've been working on. And we look at the problem very similarly, but we try to use our discrete element method with cohesive contact to see if we can get similar kind of behavior with the discrete element method. And so in these simulations, what we're doing is we completely fill this geometry with polygonal particles. We have a wind load that goes from 0 to 22 meters per second over a 24-hour period, and we try to watch if an arch develops in these simulations under different kinds of conditions where we vary the material strength in our more Coulomb failure model. Okay, so here's some initial results here where we're again forcing the model with a wind load straight down the channel, And what you can see here, going from weakest on the left to strongest on the right, modifying the cohesion term in the more Coulomb model, is that obviously we get much more breakup in the 20 kPa cohesion versus the 40 kPa. And we get a stable arch here that forms at the end of the channel here in the 40 kPa version. In this 30 kPa or somewhere between, where we get these ice arches that continue to form up along the channel, shear breakage along the sides as you would expect, but these sort of tensile-based arch failures that happen through the channel. Okay. We can look at the ice velocity through the channel, and we can see at the beginning of the simulation we get ice sort of flowing. It slows down as we reach this constriction, as you can see here in this plot, which is showing in the x-axis here the speed that we're plotting along a line, this dotted line through the channel. The red line is showing the velocity of the velocity vector in the x direction, the velocity in the y direction. So you can see here the velocity along y is changing along this midline. The velocity in x is not changing at all, which is what you would expect is fairly symmetric behavior. So it slows down as it goes through the constriction, and then it speeds back up. And then all of a sudden we start to get breakup, and we get a lot more speed starting to come through the channel, but we're still plugged here. And then at some point we obviously get a failure, and then we get a jump in the velocity here. Okay. Okay. This is sort of showing what we can sort of see, quantitatively in the videos that we've shown. Okay. And then sort of the arch formation, we found that these is really correlated to these high damage events, very similar to what Dansereau showed in their work. In this case, we were able to plot the damage rate in time, and we were able to see that when these large arches form in our simulations, they correlate to these large damage events. So there's a little bit of noise that happens at other periods in time, but these large breakage events really correlate to large damage events. Okay. We can also look at, because we use this non-local failure method, we can calculate the non-local stress acting on each particle, and then calculate the principal stresses here. And so what we're showing, similar to our velocity plots previously, we're showing plotted along this center line again, the two principal components of the stress tensor. And why this is interesting, I think, is because you can see right before the failure happens, and right before arch development happens, is that we get large tensile or hydrostatic tensile stresses after the exit of the constriction here. And we know that obviously ice is weaker in tension, and we start to get failure at this point here. So obviously compressive stresses here, all the way where we get to sort of this plugged region, and then after the constriction starts to open up, a lot of tensile stresses, and that's why we get the arch formation, I think, in this region here, this is where sort of the ice starts to fail. Other interesting thing to note here is that we can see these areas of high stress which correlate to these crack tips here. So if we visualize the stress, we can show that at sort of these crack tips, we can see that we get these high stress regions where we'd expect the crack tip driving force. Another interesting thing worth noting is that, again, using our non-local failure criterion, we can take a look at all of the particles in the simulation, plot their stress value that we can calculate for each of them, and throw it onto a principal stress space failure envelope, and then we can see that even using a discrete element method and our failure criterion, the state of stress in our simulation falls within our prescribed more Coulomb model, okay, which is actually quite interesting. And this looks very similar to what has been measured in the field as well. And then very quickly, we've looked at comparing our non-local model versus the local approach. And on the right-hand side, these are equivalent simulations, the stress calculated to do the failure on the left-hand side using our non-local model. On the right-hand side, doing local beam breakage, so the stress calculated locally in each beam. And we're finding, this is just preliminary results at this point, but we're finding that these local failure models seem to be overly brittle when compared to some of the non-local approaches that we're looking at. And this might be resolved if the local model has some sort of softening post-failure, but right now what we do is just we break it, so it's a very brittle behavior where we reach some sort of criterion in stress, and then the beam breaks. We want to look into this a little bit more, but these initial results are interesting. This has also been seen in other areas of research. This is from a paper by Andre and others in 2013 where they looked at an indenter on a discrete element, discretized, I believe, substrate, and they looked at the crack propagation using their non-local approach, which is very similar to ours, versus a local approach, and they find that these cracks develop in the local model on the left-hand side quite differently than this overly brittle sort of fractured behavior on the right-hand side. Okay. A last simulation I wanted to show is the actual Nares Strait itself. It's the very similar conditions as what we did previously with a down channel wind, only in this case it's on the channel itself, or excuse me, it's on Nares Strait itself as exposed to an idealized channel. Okay. So similar results to what I showed before. We're varying the strength of the ice through varying the cohesion in our more Coulomb failure model. And what we see, again, similar behavior as what we saw in the idealized channel simulation. We get quite a bit of breakup in the low strength model on the left, something in between in the middle, and then not a lot of breakup at all in our cohesive, our strongest 40 kPa cohesion model on the right-hand side. I mean, this is to be expected, but this is what this is showing is that, you know, the strength of the ice here, either through this cohesion term or thinning of the ice, would obviously have influence over how the ice flows out of the channel and the stability of the arches that might be able to form. Okay. We also looked at the flow size evolution in Nares Strait during our simulations for these different cohesion examples that we looked at. And this is visualized here in these three figures here, where the different colors indicate the different cohesively connected flows and their corresponding size. Okay, and you can see just qualitatively, and I'll show some plots in the next couple of slides, but you can see that we get sort of smaller flows on the left and larger flows in the right-hand side, which is what you expect when you go from weak to strong again. Okay, and so if we plot the, say, in a log-log scale, the number of flows that we found in the y-axis versus the flow, the flow size on the x-axis, we get for the weakest model, of course, we get the largest number of flows for a small flow size, and as that flow size increases, obviously it flips because this weaker model would have the least number of larger flows. And similarly, in the inverse behavior for the strongest model, we find that we have the lowest number of small flows, and as this flow size gets larger, we get the behavior that's flipped here, and the strongest material parameters result in the largest number of large flows. Okay, and we get some behavior that sort of follows kind of a power law type distribution, what you might expect, but in these channel sort of simulations, I'm not sure what the expected behavior ought to be. But this is something we want to look into a little bit more. We also looked at the mass export out of Nares Strait. We get similar sort of behavior as you would expect, just like for the flow size evolution. As the simulation starts, you know, there's no mass export out of the bottom of the strait, but as soon as the particles start to break up, obviously the weakest model, the blue, starts to export mass, the greatest and, the earliest, and continues so. And then obviously the sort of middle strength model splits the strongest and the weakest, whereas the strongest the model exports the least amount of ice out of the strait, again, which is to be expected because a more stable ice arch forms. And in these simulations, instead of using one value of cohesion, we used a range of cohesion values, so we sort of sampled. So there's some variability in the strength of the actual ice within Nares Strait. Okay, and the y-axis here might be a little confusing, but what we did just to keep the numbers smaller is we took the largest export value at about 73 hours and divided all of our values by that sort of normalizing constant. That's why we have 1 here at the top, as opposed to a much larger value in kilograms. Okay. And so obviously validation is something that we have been thinking about a lot. This is certainly not validation, but we can potentially look at some of the sort of interesting features that are happening between the, the video that we see on the right-hand side against the simulation that we've shown on the left-hand side. We get a large flow that sort of breaks away in the front, and you can kind of see that on the picture on the right as well. We get some sort of stable ice behavior in these channels, and you can kind of see that as well. This sort of shearing that happens along the coast, we get something similar here. One thing that's worth noting is that there is some breakup here in this channel, and that we don't see that behavior here. And so it's worth doing some further investigation to understand why we have a stable arch here, and that isn't actually seen in the video. There's a lot of variability year in and year out, and the sort of the action that we see here in this video on the right-hand side isn't necessarily the characteristic sort of dynamics in the strait itself, but nonetheless, I think this is worth looking into as well. Okay. All right, so in conclusion, the discrete element method does show a lot of promise for modeling sea ice dynamics at the regional and flow scale. At CREL, we've been spending a lot of work developing our discrete element modeling capabilities, in particular focusing in on how do we sort of extend discrete element approaches such that they can be used to model the breakup of larger flows, but also at the same time still capture that interparticle behavior, flow-flow contact behavior that discrete element models excel at. Okay. On the non-local approach that we've chosen to calculate stress, evaluate that stress against a failure surface, and propagate leads and cracks, at least our initial results shows that this is a promising way forward when we want to look into this further. Our future work right now, we're continuing to look at these regional scale forecasting problems, currently focusing on the Beaufort just above Alaska, continuing our investigation of this non-local approach that we went over, trying to figure out ways to do better prediction validation. And I also want to look at this idea of sea ice intersection angles, which has been explored in the continuum literature, and I want to understand if we can get variability in the intersection angles in our discrete element model as well. One thing that I didn't show today, but that we've been working on a lot, is this sort of, I guess I'll call new non-local particle-based model, this discrete element peridynamic hybrid, right? And so in this approach, we use peridynamics for the sort of larger flows and how they deform, and then a discrete element engine for how these larger flows interact with each other. And we've been getting some really interesting results with this model, and I'd be happy to talk about that as well. Thank you for your time. I look forward to talking to everybody at the workshop. Thank you very much.